Okay, once again, good morning all. In previous class, I think I have discussed very important points about SIC XC machine. Those points were instruction formats and addressing modes. And I also told you to read this next one note I had given you in the next page, which gives you clear information about these six flag bits N, I, X, D, P, E. Okay, I hope you have studied at your home. Today I go to next topic, that is instruction set. Okay, so what all the instructions are available for me on SIC XC machine? In addition to instructions which were available on SIC, here there are some more instructions are available for me to write my program, assembly level program for particularly SIC XC machine. Okay, so those instructions are once again load and store instructions, but previously we had load and store instructions only for the available registers. In SIC, we have only 5 registers: A, X, L, PC, SW. We can load and store the data into their registers and from the registers. But here, apart from those 5, another 4 extra registers are available on SIC XC. That is total 9 registers are available for me on SIC XC. Those are B, S, T, F. So these 4 extra registers are also can be used to store some data or load some data. So here some extra instructions are LDB, STB, or it may be LDT, STT, because the available registers are BS, TF. In these BS, TF, S and T are general working registers, I already told you. And in the B register is base register, and last one is F is a floating point accumulator register. So these instructions are load and store, for loading and storing the registers. And again, there are some other instructions are available for me since I have floating point hardware in my SIC XC. I can perform some floating point arithmetic operations also with the help of these instructions: add F, subtract F, multiplication F, and division F. In earlier in SIC, there were only add, subtract, multiplication, division, but here add floating point values, subtract floating point values, multiply floating point values, and divide floating point values. And next type of instructions are somewhat you want to move the data from one register to another register. For that purpose, I have one more instruction, that is RMO. It pronounced as a register move instruction. Register move instructions are used to take the operands from the register. It means that inside the register some data is there. That data, if I want to move from that register to some other place, then I can use this RMO, that is register move. Then as I already told in previous classes, COMP is for comparing register with the memory, but COMPR instruction is used to compare the one register with another register. So whenever you get a capital letter R immediately after the at the end of your instruction, so you should understand that it is a register to register instruction. In previous class, I already told you it is a register to register instruction. Similarly here, this type of register to register instructions are used to perform some arithmetic operations particularly. So again, they are add R, subtract R, multiplication R, and division R. What it means? It means that 2 registers are there. It may be S and A. Okay, in S register some integer value is there, and in A is also some integer value is there, or some other registers also you can take here. And if you want to add those content of those 2 registers, or if you want to subtract, or if you want to multiply, or if you want to divide the content of these 2 registers, then that instruction is called as register to register. And how to identify it? Just one tip I am giving you, or a trick I am telling you. So immediately after your instruction, if there is a capital R, then you should understand that it is a register to register instruction. And particularly here I am discussing about register to register arithmetic instructions. Okay, add R, subtract R, multiplication R, division R. And then one more very interesting instruction is there, that is SVC instruction. What this SVC instruction does? It is very useful to disturb our communication whatever we are having with the operating system. Suppose if we are communicating with the operating system, and suddenly if you want to stop something, or if you want to disturb that operating system from doing something, and if you want to divert that operating system, you want to interrupt that operating system, you want to disturb that operating system, then you can use this instruction, that is SVC, that is called as supervisor call. So SVC supervisor call instruction is used to interrupt the operating system, the communication with the operating system. Very rarely we use this one, don't worry about it. Okay. Next topic is the last topic of SIC XC machine is input output operation. If you remember in SIC, we can perform input output operation by replacing rightmost byte of register A. Okay, rightmost byte means actually every register is a 24-bit length. 24-bit length is nothing but 3 bytes. So in these 3 bytes, if you remove and if you put some extra zeros and ones in a rightmost byte, that is rightmost byte is nothing but rightmost 8 bits. So if by replacing the rightmost 8 bits, we can perform input output operations there. And to do this input output operation, we have there two major instructions, RD and WD, read data and write data. Before executing RD and WD instructions, first we should check whether my device is ready to read the data and whether my device is ready to write the data. So how to do that one? For that one, I have one more special register, that is TD, that is test device. And the result of this test device instruction will be stored in a condition code CC. If the condition code is equal or equal mark, then you should understand that your input device is or output device is not ready to read or write the data. Okay. So similarly here, in addition to these instructions, PD, RD and WD, in SIC XC, we perform this input output operations by using some input output channels. This word is very important. Here I am showing you with the mouse cursor. This word is very important. Here in SIC XC, we perform input output operations with the help of input output channels. But what about in SIC? In SIC, we used to perform input output operations with the help of CPU only. But here, CPU is not performing input output operations. CPU is busy in executing some other instructions. So these input output instructions or input output operations will be performed by these input output channels. Okay. And because of this only, that CPU can concentrate completely on the execution of the program or executing some important instructions or some important logic of the program, but completely to perform input output operations, the input output channels are dedicated here. Okay, input output operations will be completely taken care by input output channels, and these input output channels as well as our CPU, they both together will work parallelly and simultaneously. Because of that only, it is going to reduce the workload of the CPU. Okay, and by reducing the workload of CPU and by executing the input output operations parallelly along with the CPU, so we are going to get an efficient system. Okay, it means that we are going to get the fast system. Okay, so here input output channel helps the CPU, thereby reducing the workload of that CPU. So input output channels and CPU, they perform simultaneously, thereby increasing the efficiency of the system as well as the speed of the system. Okay, so here to start these input output channels and to stop these input output channels, there are three very special instructions are available for me. So those instructions are SIO, that is start input output, TIO, that is test input output, and then HIO, that is halt input output. Start and halt. Start is used to start the input output channels to perform its operations, and halt is a stop the input output channels to perform. And the test is so to test whether my input output channel is working properly or not, whether it is performing input operation and output operation properly or not. I have one more instruction, that is TIO, start, test and halt. These are the three instructions what I have to perform input output operations through these input output channels. Okay. So this is about SIC and SICXC machine. Next, let us go to next topic. There are some programming examples I will show you. Very interesting. You should listen to me carefully and you should observe my slide carefully, because it is difficult to teach these programs in online class. Okay, but still I try my level best. You just keep on observing this mouse cursor on screen. The first program is to perform some data movement. Okay, so simple, very simple program it is. I want to move the data from one place to another place. That place may be a memory or that place may be a register. It means that I may move the data from memory to register or register to memory. So to do this one, I have written two programs. One is for SIC machine, and for your easy understanding purpose, I have made two columns here. Right side, I have written the same program. If I write in SICXC, how it looks like. Okay. First, we will see the SIC program. That is, first statement is LDA. Okay, LDA, and here F5E is there. What is this F5E? This F5E is just one operand. Instead of F5E, you can write any operand here, no problem. It is just like a variable name. So here, what is going on here? Here, in this variable, whatever the value is there, that value is stored in the register A, or that value is loaded in the register A. Okay, then store A, STA alpha. Alpha is also an operand. In A, whatever the value you have, that value you are going to move into the variable alpha. Okay. Now alpha has some data. Okay. Now we will see next. Now you have moved some integer value. Now I want to move character value. As I already told, in the data formats, I can only store integers and characters in my SIC. I can use only integers and characters. I cannot use a floating point. So here in the first two lines, I have moved integer value. In next two lines, I am going to move one character. Which character I want to move? One variable I have taken here, char z. Okay, instead of char z, we can use any variable name here, any operand name here, no problem. Okay, and here particularly I want to move one character which is a capital Z. Suppose, for example, capital Z is a one character which takes 1 byte of data. Okay, char size is what? 1 byte. So I want to move it to register A. So I use LDCH, load the character. Even though capital A is not here, it is invisible, but capital A is present here. So that character Z will be loaded into the register A. Then STCH, what this STCH does, it moves that data from register A to one more variable. That variable I have just named it as a C1. Okay. Now the C1 content is capital Z. Is it clear? These are just simply 4 lines of program it is. After that, some gap I have given, and again I have written some 4 lines. So always remember, the assembly level program is divided into 2 parts. Here, first part, whatever I explained now, these first 4 lines are actual logic of the program. These are actual logic of the program. But what about these 4 lines? These 4 lines are called as storage defining part, or it is just like our declaration part in our C program, for which variable, what amount of memory you are reserving, and in that variable what value you are initializing. So we do this in a declaration part, no? So similarly here we are doing that in a storage defining part. So every program in SIC or SICXC is divided into 2 parts. The first part will be always logic, and the second part will be storage defining part. So here, what all the variables I have used in my program, for those variables I am reserving some amount of memory, and in that memory, if possible, I am going to store some value. I mean, I am going to initialize that variable. So let us see first one, alpha, reserve word, and 1 is here. Always remember, RESW, reserve word, will reserve how many number of words in memory? In this third column, whatever the number you write here, that many number of words will be reserved by this instruction. Actually, it is not instruction, it is called as assembler directive. I am using one new word today. It is assembler directive. Okay, I will discuss about these assembler directives in the next slide. Don't worry. RESW is a assembler directive. It is not part of logic of your program, but it is part of your program. It is not part of logic of your program. Okay, these assembler directives are used to reserve some memory for particular operands or variables. So here my variable is alpha. For this alpha, this reserve word assembler directive will reserve one word of memory. Okay, one word of location or storage. In that location, which value we are going to store, I have not written here. Okay, so in that one, what value we are storing? We are storing some value which is present in the variable 5, because 5 is moved into A, and from A to again it is coming and sitting in the alpha. Okay, so what value we are storing here, I have written here. Next line, my next variable or operand is 5. Okay, instead of 5 you can write anything here, beta, gamma, or your name also you can write here, no problem. Simply I have written it as F5 VE, capital F5 VE, and it is just one variable name it is. And for this variable, one more assembler directive is used here, that is word, WORD. You just make a group of these two. This is a reserve word, but this is only word it is. This reserve word reserves how many number of words? Here in this third column, whatever the number you have written, that many number of words it will reserve in your memory for this alpha variable. But word, what it does, word will reserve exactly only one word in memory. One word is nothing but 3 bytes. It reserves only one word. And in that one word, which data is stored, directly I will write in this third column here. Okay, here I have not written a data which is stored in this word, but here I am storing some value which is stored in this word. That value is a 5 integer value. It means that in F5E I am going to store this value. So because of that only here I told you, here F5E is there now. This is reserved with one word, and in this F5E I have stored 5, and that 5 integer value is stored into the register A, and in next instruction that A content, that is integer value A, is stored into the next variable, that is alpha. Now the value of alpha variable is 5. Keep it in your mind. Okay. Next 2 lines are also very interesting and similar. Instead of integers here, I am going to load and store character data. And particularly which character? I told you here only I am going to store one character Z. And why sir Z only? It is not compulsory. Simply I have written here Z. You can take any alphabet here, no problem. You can store any character, no problem. And here also two very important assembler directives are there, byte and reserve byte. Here reserve word was there, no? Similarly, here also one reserve byte is there. What it does? Reserve byte will reserve how many number of bytes you want to reserve for a variable C1. How many you have written here? One you have written. So RESB, reserve byte assembler directive, will reserve 1 byte of memory for the variable C1. Okay. Next here BYT is there, like word byte. What this byte does? Byte does exactly 1 byte of memory, and in that 1 byte of memory, which data you are storing, you have to write in third column itself. Okay, so that is you are storing the character Z, and always simply you cannot write only Z here. You should mention it as a character constant, right? It is a character constant. Z is a character constant. To indicate it is a character constant, you should enclose this character inside a single quote, and this character should be prefixed with a capital C. Then easily I identify it as a character constant. Remember. Okay. Similarly, in our next programs, sometimes in the place of C, we write here some capital X, capital X, and some binary numbers or hexadecimal numbers will be written in the place of Z here, and they will be enclosed inside a single quote. At that time, you should understand this is not a character constant. This is a hexadecimal code or hexadecimal constant. Okay, if it is a capital C, you should understand it is a character constant. If it is a capital X, you should understand that it is a hexadecimal constant or hexadecimal value or hexadecimal code. Clear? Reserve word will reserve the number of words. How much you will write here in this place, third column of your program. Okay, but the word will reserve exactly one word. In that one word of memory, what data you are storing, you will write in the third column. Okay, and byte will reserve exactly 1 byte of data in the memory. Sorry, exactly it reserves 1 byte of memory, and in that 1 byte, which data you are writing, you are storing or you are saving one character. That is, one character is nothing but 1 byte. So that character is Z, and the reserve byte will reserve 1 byte of memory here in this particular example. It will also reserve the number of bytes in a memory. That how many number of bytes you want, you can write here. Instead of one, you can write 2, 3, 4, 5, 6, 7, whatever it may be here. So whatever the number you write here, that many number of bytes will be reserved in your memory for the variable C1. Similarly here, instead of writing 1, you can write 2, 3, 4, 5, something else. How much number you will write here, that many number of words will be reserved by this assembler directive RESW for the variable alpha. But this word and byte, whatever you write here, they will reserve only one word, and it will reserve only 1 byte. In this one word, what data you want to store, that you should write here. And in this 1 byte, what data you want to store, that you should write here. Clear now? So this is very simple program to move the data from one place to another place. One place to another place means here I am using LD. It means the data, integer data 5 is moved from memory to register, and in ST instruction, the integer data 5 is moved from register A to memory. Okay, that memory is nothing but here variable alpha. And then in LDCH, the character Z is moved from memory to register A, and in STCH, the character Z is moved from register A to the memory or variable or operand C1. This is just a data movement operation we are doing here. I hope you understood everything. Very simple program written in SIC machine. Okay, the same program, if you write in SICXE, it looks like this. Because of so many facilities and instruction formats and instruction sets are available for me, I have written this program like this. So here I have written LDA hash 5. So already you know that you want to store the value 5 in a variable 5. So no need to write it as a variable. Directly you can take that value 5 as an integer value and you can store it into the register. You can load it into the register A, and that integer should prefix with the immediate addressing mode symbol hash. Okay, immediate addressing mode it is. This instruction is in a immediate addressing mode because this operand, this integer operand is a beginning or prefix with a hash symbol. So here 5 value is loaded into the register A, and in next instruction that 5 value will be stored from A to the next available variable, that is alpha. Now the value of alpha variable is 5. Clear? So here I have not used a separate variable or operand F5E or something else to store the value 5. Directly I have taken that value here and I have loaded into the register A, and from register A I have stored it into the alpha. Clear? Similarly, in next two steps also I have instead of LDCH I have used here LDA. Once again it means that I want to load integer value instead of character, and that integer value is 90 here. Directly 90 I have taken, I have loaded that value into the register A. Why I have taken 90 directly? Because 90 is a ASCII value of character Z. Remember, if you want, you open your ASCII value table in Google and you find it, the capital Z. Okay, character capital Z is that character's ASCII value is a 90. Okay, so directly I have taken it as a 90 and I have loaded into the register A. Then the next I will take STCH. I store that character because when it comes to this 90 as into the accumulator register, and then it will be converted into the character, so that character will be stored into the variable C1. Okay, STCH stores the character from the register A to the memory C1. Clear? Now here I am using only two assembler directives in my declaration statement or storage defining section, that is RESW, reserve word. What it does I already told you. It reserves whatever the required number of words you want to reserve in memory, that many number of words it will reserve. But here if you want to reserve only one word, that is 3 bytes, then you will write here 1 byte. One word, or else you can write 2 also here, 3 also here, whatever you want you can write. That many number of words will be reserved for the variable alpha. In alpha you are going to store simply one integer value 5. As I already told, in this SIC or SICXE, integers are stored in the form of 24-bit binary numbers. 24-bit is nothing but 3 bytes. 3 bytes is nothing but 1 word, and 1 word is sufficient for me to store this integer value. So I have reserved only 1 word here for alpha. Clear? Next, reserve byte. Reserve byte will also reserve whatever the number you write here in this place, that many number of bytes will be reserved. Here I want to store one character Z, so simply 1 byte is sufficient for me. So I have reserved only 1 byte here for the variable C1. Okay, so here I have defined alpha and I have defined C1. I have not defined a 5 variable. I have not defined one more variable char Z here. Clear? Because directly I took this 5 as an integer value here with the immediate addressing mode facility in SICXE, and this Z I have directly take its ASCII value and I have stored it into the loaded into the register A with the help of immediate addressing mode once again. Clear? So this is very simple program for SIC and SICXE. Just try to understand the difference between SIC program and SICXE program. So what are the advantages of using SICXE machine, and what all the additional instructions and facilities are available for me in SICXE. Just see immediate addressing mode is playing a very important role here to reduce my program's size as well as to make my program efficient. Okay, next we will go to next program, that is a arithmetic operations. Arithmetic operations in SIC and SICXE. So first I write a SIC program, then I write a SICXE. Okay, you just focus on the left side column to perform some arithmetic operations. Here, what arithmetic operations I want to do is simply I tell you one equation I want to do here. So that equation is arithmetic equation. Just a minute. See here. I want to evaluate this instruction, this expression. What is that expression? Alpha plus increment minus 1. This expression I want to do. Okay. So after that, one more expression I want to do. This expression, whatever it gives us, the result I want to store in one variable beta. Okay, remember, this is my first task. Alpha plus increment minus 1. Whatever the value it will give me after evaluation of this expression, that value I want to store into the variable beta. This is my first task. My second task is similar, one more expression I want to evaluate. That expression is gamma plus increment minus 1. Its result I want to store in the variable delta. Okay, these are my two tasks what I can do with arithmetic operations. Since I am performing arithmetic operations, I should use a register A here, accumulator register. So see here how nicely I am doing it. LDA. So alpha, I am storing it into the A. Before going to this one, first let us see what all the variables we are defining here. Okay, first directly come to storage defining section. Word is here. Word assembler directive. What this word will do? This word will reserve one word of data or memory. It reserve one word of memory. Okay, in that one word, and which value I am going to store? It is also one only. Okay, so because one is one integer value which is stored in a 24 bits of binary value, binary numbers, and that binary numbers are zeros and ones. So here one I want to store in the form of 24-bit binary number, and that 24-bit is nothing but 3 bytes. 3 byte is nothing but one word. So that one word I am reserving here for the variable ONE. Instead of ONE, you can write your name also here, no problem. It's just a variable name. In that variable, which value you want to store? You want to store one word of data. Okay, that is one only you are going to store. Then reserve word. Reserve word will reserve whatever the number you write in third column, that many number of words will be reserved by this reserve word for the variable alpha. Here simply I am going to reserve one word for alpha. Okay, then the beta. Beta for reserve, for beta also I am going to reserve one word, and for gamma also I am going to reserve one word, and for delta also I am going to reserve one word. For increment variable also I am going to reserve one word here. That's all. Clear? Then in one word, that is for reserved for variable 1, which value I am storing in this one? I am going to store this value, integer value 1 I am going to store. Remember. Okay. So these all are not values. These all are a number of words reserved by RESW, 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 RESW. But this one is nothing but, it is not indicating number of words. It is indicating the value which is stored in that word, one word, and that word is reserved for variable 1. In this variable, I am going to store this integer value 1. Remember, LDA, LDA alpha. From alpha, you are going to, sorry, next. Okay, see, in alpha, whatever the data is there, that data here, actually I am not storing any data in alpha. So alpha will be loaded into register A and add in a register A only. Already alpha is there. To that alpha, I will add increment. Then that expression will become alpha plus increment. Okay, alpha plus increment I achieved now. Now I want to do subtract. Subtract minus 1. So then this equation becomes alpha plus increment minus 1. Now I want to store it into the variable beta. Though now whatever addition and subtraction you had done, that all result will be stored in A only. You are doing this all circus in A only, register A only. Now you store that result into the variable or operand beta. Now the expression looks like this. Beta is equal to alpha plus increment minus 1. Clear? Similarly, one more expression I want to do. Gamma is loaded into the A and you add increment into the A, and in that A, the expression looks like this, gamma plus increment. Now you subtract 1 from that. So now that expression becomes gamma plus increment minus 1. Then this every expression, this complete expression, I want to store into the one more variable delta. So store that content of register A, whatever it was, you store it into the delta. So now the expression becomes delta is equal to gamma plus increment minus 1. Understood? Very simple and interesting programs. It is written in SIC machine. Now let us see how we can write it in a SIC XE. If you observe one thing here, increment is common in both the expressions, INCR. Okay, here also INCR is there. So again and again, whenever I want to evaluate my expression, again and again, I no need to take it from the memory. I no need to take it from the memory. I no need to read it from the memory. So for temporary purpose, for some amount of time, at least you store it into one general working register, yes, and directly you can take that INCR from that register, yes, instead of again and again taking that INCR from the memory. Okay, that we are going to achieve here. See here. My first statement of my program itself is a LDS INCR. What it means? You are going to load INCR in a general working register. Yes. Now the content of yes is INCR. Remember, whenever I want INCR, just I use this register yes. Clear? Instead of using or calling this INCR from the memory, I just use the register yes. Clear? So here, my first program, the next line is LDA alpha. Alpha is loaded into register A. Then in register A only, I perform addition operation. That is also register to register arithmetic operations. Just now I told you in instruction sets, I have this instruction add R, which is a register to register instruction, particularly register to register arithmetic operation instruction. So I want to add two registers, A and S. In A, alpha is there. In S, increment is there. So the expression becomes alpha plus increment. The alpha plus increment expression will be stored again in the register A only, and now you subtract 1 here. Since you know the integer value already, directly you can write it as a #1 here with the immediate addressing mode. So the expression becomes alpha plus increment minus 1. So this complete expression is present in a register A now. Okay. Now you can store that content of register A to the variable beta. Now that expression becomes beta is equal to alpha plus increment minus 1. The same type, one more operation let us do here. Gamma I will load into the register A, and in register A I use register S. So for performing addition, I use ADDR A comma S. Then it becomes gamma plus increment, because what is the content of register S? Register S is increment here, right? So here I am using that register directly. So gamma plus increment, then minus 1. So this complete expression is stored or is present in a register A. Now I store that register A content into the variable delta. Now the expression looks like this. Delta is equal to gamma plus increment minus 1. Clear now? So everything is same here. Instead of defining or reserving one word of memory for the variable 1, directly I have taken that 1 as an integer value here with the help of immediate addressing mode. So here no need to define this variable ONE in SIC XE. So only remaining variables I have defined here. I defined alpha, and for alpha I am reserving one word, and for beta I am reserving one word, for gamma I am reserving one word, for delta one word, for increment also I am reserving one word. Okay, I am not defining ONE in SIC XE. Clear? So this is about SIC and SIC programs to perform arithmetic operations. To make you clear difference about SIC and SIC, I have written side by side here only by using two columns. Okay. Next, indexing and looping operations in SIC and SIC. You know, in our C program, we use for loop, while loop, and do while loop. Same type of operations we can do in SIC and SIC also. How to do that, I am going to explain you here. Just to see, very interesting topic. Actually, I think here I am going to use do while loop. Okay, do while loop. And what is the main problem of this program? What is the main objective of this program? See, let us consider two strings, string 1 and string 2. Okay, string 1 and string 2 you have, and string 1 contains some characters. It means it contains one string. For example, you consider VSMIT as a string 1. Okay, VSMIT, how many characters are there? 5 characters are there. And string 2 is completely blank string or empty string. Now the task is we have to copy that string 1 to string 2. It means that what all the characters are present in string 1, I have to copy them into string 2 one by one. How many characters are there in string 1? 5 characters are there. V, S, M, I, T. One by one, I want to copy these characters from string 1 to string 2. So how to do it? Very interesting. Let us see here. See here. First instruction is LDX. Okay, LDX. Oh, sir, why you are using X here instead of A and other? See, X is already I told you it is an index register. So in looping also we use the index now. If you take your for loop only, there we use one index variable I, and every time we increment it, correct? Same thing here also I want to use here. So in register X, I am going to store load one value that is 0. Okay, so I am initializing the index value, index variable, index register X to 0. So how you are doing it? So first come to this data storage variable defining section here. So I define one variable str1 string 1, and here assembler directive is a byte. What it does, it reserves one byte of memory for the variable string 1. Okay, and in that 1 byte, what I am going to store here? I am going to store one character constant. And since in this character constant in the single quotes, there I have written a test string here. So just remove this test string and you just imagine VSMIT characters in the place of a test string here. Okay, so it is a character constant. So since in this character constant, within 5 minutes this meeting will be completed, and after 5 minutes you rejoin one more class. I continue today. I take Avadut sir's WT class today. Okay, within 5 minutes, if this meeting ends, you rejoin with the same link. Okay, see, in register X I have stored 0. Okay, how 1 minute, I was here, no, byte. So it reserves 1 byte actually, but here since there are 5 characters are there, VSMIT, it reserves 5 bytes now. So remember here how many number of characters you write, that many number of byte will be reserved, particularly when you are using character constant. I am telling, if it is a CZ, only 1 byte will be reserved. Okay, but here I am telling you VSMIT 5 characters are there, so 5 bytes will be reserved by this byte for the variable string 1. And next string 2, for string 2, RESB reserve byte will reserve 5 bytes. Here number of bytes how much I want, I have written here. It reserves 5 bytes. Here I have reserved 5 bytes, and here also I am going to reserve 5 bytes for a string 2. But this one string 1 was reserved by using a byte. but string 2 is reserving with the help of RESB. Because byte, why sir you have written byte? Because whatever the number of characters here you write, that many number of bytes it will reserve. But in that byte, what all the data is stored also we write here, right? VSMIT, that value is stored in the str1. VSMIT is the content of string 1 now. Remember, okay? String 2 is blank now, right now. Only 5 bytes are reserved for string 2, but it is initially empty. We are not writing any data here. Correct? We are just writing how many number of bytes you want to reserve. Where I want to reserve 5 bytes, so I have written 5 there. Okay? Then word, what it does? It reserves one word of memory for the variable 0. Instead of 0, you can write any value here, any variable name here. In that variable, which value I am storing? 0. Clear? Then word will also reserve again one word of memory. In that, for which variable it is reserving that one word? It is reserving that one word for the variable 5. Instead of 5, you can write anything here, no problem. And in that one word, what value I am going to store here? I am going to store 5. So remember, the value of the variable 0 is 0 and the value of the variable 5 is 5. Is it clear? Now, the value of the string 1 is VSMIT, the value of a string 2 is nothing. Right now it is a blank. Okay. Now, let us wait for the end of this meeting. Next I continue. Okay. Just wait for 5 minutes. I end this meeting and again you can rejoin.